So thank you all for coming. We're worried that we weren't going to fill the seats, but it's good to see you all here. So before I officially start, I'll go over a bit of a overview of myself and how I got into 3D printing. So I'm studying the Masters in Medical Physics at UWA. I've done one semester, as Pejman said. And during the summer break, I thought, look, I'll come in, I'll get started on my research proposal and get a head start. And so things didn't quite go to plan. I got a little bit distracted. I walked in the office and saw these two printers sitting there. So we've got the Mini here on the left and the MK3S Plus on the right there. And I was a little bit intimidated by them at first. I didn't want to touch them. I thought, I'm probably going to break these things. I don't know how to use them. But Pejman said, yeah, have a play around with them. Don't be scared of them, and they might be useful in your research. So first thing I did is I read the instruction manuals for both of them. I started doing some of the basic prints that are on the USBs. Then I started downloading some models online and printing them out. And now I've done some of my own prints. So that Phantom there you can see on the left, the cream-coloured one, that was took about 32 hours total, 4 different pieces. And I'll go into that a little bit later in a slide. So yeah, after all those prints and many failed prints too, which we have a few to show you guys, we've learnt quite a lot, quite a few skills along the way. And we've kind of tried to condense them all down into this workshop, and that's what we'll be showing you today. So I'll let Riley introduce himself, and then we'll jump straight into it.
Cheers. So, hey, I'm Riley. I started in 3D printing because it was part of my project. I came in, talked to Pejman about it. He said, we're doing this 3D printing thing. I don't know if you'd be interested. And I thought, that sounds really cool. So I decided to jump on board and I started doing the printing. We ended up getting these 2 printers at the end of the semester. And so I was able to start playing around. Like Andrew, I started printing some stuff. So I printed out that face over there, and this nose, and a couple other bits and bobs. And it's been a lot of fun. It's part of my project. And yeah, and I mean, we're both UWA medical physics postgrads. So, and other than that, Andrew can start the talk.
Yep, we'll just jump straight in.
Yeah.
So I'm going to start off with some applications of 3D printing, and maybe there's some in there that you guys won't expect. So the applications are very widespread. Starting off, you have custom manufacturing. So kind of typically mass manufactured products like phone cases can now kind of be custom designed by the user for their own liking. So Nokia first did this, I believe, in 2014 with these phone cases. They released STL files that you can modify yourself, and then either you print at home or they'll print and send out to you. I'm not sure if they still do it. That's definitely a big part in 3D printing. Yeah, the aerospace industry. So I don't think there's any aircraft that they use for crucial parts, but certainly in the aircraft. And they've actually made a 3D printer that can operate in zero gravity conditions. So I didn't know that before I was writing this presentation. I found that really interesting. And not just plastics, but this is also a bioprinter. So you can print cellular makeup. So essentially they've printed a heart. It's not a functional heart, but they've printed a small neonatal heart. You'll see it in another slide from now. So I thought that was also pretty cool. The automotive industry, they have a pretty similar application of 3D printing. So not any critical parts. They do a lot of rapid prototyping. So that's when they just make a quick model with 3D printing. It's quick, it's efficient, it's cheap. And then until they get their desired design, they can do it that way. I've heard some people use 3D printing to replace parts of the engine, but I wouldn't recommend that. There are some filaments that can take well above 200 degrees Celsius, so they are quite strong, but I certainly wouldn't recommend replacing parts of your engine with 3D printing parts. Food. So that's a kind of crazy one. They first started printing sugars and chocolates, making little chocolate houses. And now I think they can print meat on a cellular protein level. I think that's still definitely in the research phase. That's very interesting as well. Fashion. That dress there is fully 3D printed in, I think, around 2011, 2012. A Dutch designer, Van Herpen, they made a whole entire dress 3D printed. It took about a week. And that's been modeled in the catwalk in Paris and Milan. So definitely really widespread. And I think probably another area that you are more anticipating is the medical area. And that is one of the biggest areas 3D printing has kind of came into. I'll get into that in a little bit more detail. So it's a $1 billion industry. In 2014, it was around, I think, $400 million industry. And as of last year, it has reached around 1.4 billion, and that's just going to keep growing. Prosthetics, that's a huge one. So they printed out hands and parts of lower arms. In 2014, a 5-year-old girl was the first to receive one of these prosthetics. She was born without fully fused hands, and what they did is they put in this kind of prosthetic, and they've got electrical components there that integrate into the nerves of the arm, and she can have some really rough motor control, but I think that was a pretty neat thing. Lower jaw for people, I know that they've done that. And another interesting one is animals. So that eagle there, they printed out a prosthetic beak for it. I thought that was pretty amazing. Fighting coronavirus, yep, so a company, Isanova, in Italy, they printed out 100 respiratory valves in about 24 hours for a hospital that needed it. That's great. Tissue and organ fabrication, as I said before, on that bioprinter, that zero gravity printer. I think there's definitely much more advanced tissue and organ fabrication than that, and since then, that was in 2018, so, yep. And then absorbable surgical screws is another one I've put up there. These are just a few examples. There's many, many examples in the medical industry, but these screws can be printed, customized for, and this one was an ACL surgery, to hold it in place for recovery, and then it gets absorbed by the body afterwards. Alright, so this is a bit of a shameless plug, a bit of research that I've been working on in the last few months. It's not my main project, but as I said, I got very distracted. So what we did is there was a CT scan of a patient. There on the left, that's in a program called Slicer. And so we rendered that into a 3D volume, created a 3D model of it, cleaned it up a little bit, sliced it into quarters, and then printed it on the printer. And that's it just there. You can see it on the very right. We've spray painted it now. We're going to fill that with water and do some research on that, as well as a 3D bolus. So I think a lot of you here will know what a bolus is. It's typically flat, and the problem with that is on the patient's surface, the patient isn't flat. They have little changes in their geometry. So using that same file, we extruded the geometry and made a little mold, filled that up with Uracil, and yeah, we actually made a custom bolus, and that's really the whole point of the research that we're doing. That's the bolus just there. And it should be tissue equivalent, just like a normal bolus, and it fits nicely on the patient. Okay, so now I'll hand you over to Riley.
Thanks, Andrew.
Yeah.
So just a bit more about the background of 3D printing. So what exactly is 3D printing? So 3D printing takes a virtual object and then creates it in the real world, often out of plastic, and then that's called additive manufacturing, and that's because it builds it up layer by layer, instead of subtractive manufacturing, which is like chipping away at something until it's the shape you want, say like ice sculpting. Some typical filaments that people use are PLA and ABS. These are the common ones that everyone uses. They're widespread, relatively easy to use. We typically use PLA because it's a bit easier. ABS can be a bit temperamental, and it suffers some more temperature effects because it's printed at a higher temperature. And just some software side of things. So we have STL and Gcode files, so we'll talk about those a bit more in a little bit. And then slice programs, which is how you take an object and make it into something that can be 3D printed on these machines. So components of a 3D printer. So here we have the print head. So this is where the filament comes through that Bowden tube, enters into this where it gets heated, and then there's a little bit just here, a bit hard to see, that splooges out the filament as a sort of molten form, which then hardens and then is built up layer by layer. We also have the heat bed, so this is heated and allows, so that way it doesn't like immediately shrink because of the change in temperature. Here we have a control box, so this is where you would load the print, decide some of its settings, adjust these axes depending on what the print is doing. And then we have these axes and these motors, so this drives the printer left, right, up and down, and then the printer also moves up and down by itself. You might be wondering why these printers. So this is a Prusa Mini, which you can see over there. So Prusa are a good company. They have a lot of open source programs which make it a lot easier to use, as well as being cheap and affordable. And also, what was it? They, mind blanks. But otherwise, Prusa, nothing. Sorry. I'm completely forgotten that point. Let me, it self-levels and does a check whenever it prints to make sure there's no warping of the heat bed. So just a bit more about the movement. So as you can see, the heat bed moves up and down, which defines the y-axis. The print head itself moves along this axis to define the x, and then the whole print head and axes moves up and down to define the Z. And this is achieved through motors, belts, and the heat bed. And because of this, it can do complex shapes such as circles, hexagons, cats, phantoms, whichever you want. So the printhead, a bit more about it. So we have the extruder, so that delivers the melted plastic. So that's this metal bit here. We have the cooling fans, so that makes sure that this doesn't overheat and gets ruined. We have the axes, so that these metal things, which help it move left and right, or in the other case, up and down. We have the feeder, so that's this bone tube and this nut. So that helps pull the filament in, so that way it can be melted and then extruded. And then we have the sensor, which is this bit here, which senses the height above the heat bed. So that way it's making sure that it's at the correct layer height, so it's not just causing essentially one of these, where it's completely gone awry. I believe that is, accessories. So obviously there's printing started out as a hobbyist activity. And so there's a lot of self-modifications you can make to a printer. So for instance, a dry bag or a spool holder, which we have one over there. So that keeps the filament dry and offers better prints. You can have sound dampening legs, so that makes it a little less noisy. So if you have it in the office, you don't get death from the thing moving up and down. Stabilizers, so in the case of the Mini, you notice it doesn't have the other side rail to hold it steady. That causes, so you can add on this bit, which will help stabilize it and stop it from twisting. And then nozzle variations. So each nozzle you can change is the thickness of the hole where the material comes out. And so that can help change some aspects of your print. I believe now I'll be handing off to Andrew. No worries.
All right, so before we start printing out 3D models, we kind of have to know what they are. So I'm going to go over a bit of theory, so don't worry, it's not going to go too deep into it. So STL, just a bit of history behind the file format and what it is. So STL stands for stereolithography, which is a form of 3D printing, where the 3D object is created layer by layer using a photochemical process. So that's not like these printers here, we use filament. So you do have resin printers where they have a tub of resin, as you can see just there. And what happens is it shines a laser onto the resin and it forms chemical polymers out of the monomers and solidifies it layer by layer and pulls the whole object up. And so this is the original kind of 3D printing where STL files were made for. The AutoCAD, the CAD software was using this STL files, but we still use them in these printers because they're simply just a file that defines an object's geometry using triangles. And so I'll go into that on this next slide. So in red, you can just see it around the outside, there's 2 rings. And so that's your CAD model or any model. It can be as complex as you want. This one's in 2D, so it actually is impossible to print, but you'll get the idea of what an STL model does. And so an STL model is an approximation of this model using a series of triangles. And so the more triangles you add to your approximation, the more accurate to the circle it's going to be. But then the bigger the file will be and more likely for errors in really complicated meshes. Yep, so each triangle is defined by 3 vertices and a normal vector. And the slicing programs we'll go into in a second, they work by converting these STL objects slice by slice into instructions on how the printer has to move, extrude, the temperature, and so on. And these slicing programs can't do it if your STL model is faulty. So if it's got a hole in it, if it's not well connected, it will chuck you up an error. And I had a big problem with this. I was trying to figure out why is it doing this. I should just be able to print with an open surface. And so I just want to make a bit of a clarification. You can put holes in a model, like a tube that goes all the way through. I believe Riley's got one there. Yeah. So the thing is like this, you can imagine a donut. It's still closed, and it's not a hole in the sense that it's a hole in the shell. So you can't have a hole in the shell of the STL model. So if I took out, say, 2 of these triangles just on the side here, those 2 there, it would not be able to print. But if I took those 2 out and then wrap this side all the way back around underneath, then it is a closed model and we can print that. So that's just something to look out for if you ever get that kind of error. And so on the next slide, I will show you another reason for why we have to have a closed and connected object, and that's so you can print with variable layer height. So that can change your resolution of your print. I'll get into that on this next slide. So first of all, I'll go over some examples of closed polyhedrons. So that, it sounds a little bit technical, and I got that from Wiki. But that's a first example, tetrahedron, simplest one. Just 4 faces, very simple model. small stellated dodecahedron, so that's got 200 triangles. If you count all those triangles, you'd say that's not 200, and that's right. But in this model, that's the triangles are actually placed onto, I think, hexagons or something like that, which are made out of more triangles. So that one there contains 200. And then Calicat, I don't know, a hedron, whatever you want to call it. We've got quite a few here. You can see them. These are really good for doing calibration. A lot of people use a cube, but I think it's a bit cooler having a cat. And you get to tell a few basic things from your Calicat print, like overhang, which Riley will get into later. And we'll be printing one of these midway through the workshop, so look forward to that. So why do we care about these polyhedrons in STL files? Well, as I said, incomplete or broken models will be unable to be sliced by the slicing software. And also so we can have variable layer height. So I'll just show you what I mean by that. So if that's your 3D model, that's just a basic slab. I think it's about 2.5 millimeters high by 25 millimeters by 25 millimeters. And in the slicing program, say we want the printer to print that out with a layer height of, say, 0.25 millimeters. So that's actually quite rough. Well, when you do that, it will divide it up into 10 layers, so 10 times 0.25, 2.5 millimeters, and you get that result. But if we want to split it up, say, into 50 different layers, so we can get a much finer resolution, it doesn't matter much for this slab, so maybe not the best thing to show. It's something like a sphere. If you're going to print a sphere, you need really high resolution, so low layer height. And so that's how the slicing software is able to do that. You need a closed and connected 3D object. So most of the time, anytime you download an object online, it should be fine. But when you're making your own ones and they get more complicated, or you're converting from a CT file, that's something you do have to look out for. All right, so speaking of Gcode, Riley will run you through that a little bit.
Cheers, Andrew. So Gcode, it's a type of programming language that's specifically built for machines to read and use. As you can see, it's very not friendly. I mean, like these G's and M's are all functions, but they're not named or anything. They're just identification letters, and so it's pretty unusable if you want to actually write in it. And also, this is just movements. If you were to print, there'd be another variable, which would be E for extrusion. And so, to get around that, we have slicing programs. So that will take the STL files Andrew was talking about, and they will slice them to produce a Gcode, which the printers can then read to then print the objects we want. So using the Prusa slicer, so I'll be just going to a bit of a live demo now. So let me switch to it.
Yeah, while Riley does that, I'm actually going to preheat these so we can print something in time.
So here we have the Prusa slicer. So this is a program provided by Prusa that works with their printers. So if we click on over here, the top left, we can import objects. So these are all STL files, and then open up. So we have a dodecahedron that's hollow. So we can move around. And so with this shape, we can do a lot of basic movements to it. So for instance, if we click over here, we can move it. And so then we can then move it up by clicking on it. We can move it using these. And then we can also type in the position we want over down by the bottom right. Similarly, we can scale it. So we can use individual axes and scale it along those. Or we can use this square and scale it as a whole object. And then again, you can use it down here. And then, so if I type in 130, and then it'll make all of those 130 as a constant shape. And then rotation, very similarly again, you can rotate it along either or. I believe there should be if you go along this bit here, you can do exact angles of multiples of 5. But if you go out here, you can then just do kind of any angle, but it's a lot less precise. So if you want to do like exactly 90, it's always a good idea to stay here unless you're really accurate with your mouse movements. Other than that, these are all sort of the basic ways of manipulating objects within Prusa Slicer. I believe we will be starting the print. No, it's a bit later, sorry.
Yeah, I think in another slide now.
Yep, all right. So
How many people brought their laptops? I know we didn't tell you. We forgot to. Yeah.
So, oops.
And do you guys have Prusa Slicer? All right. Yeah, if you want to open it up, we might do that because it's good to have a bit of actual hands-on experience with it. But if you don't have your laptop, don't worry. I'll have the images up in the slide so you can follow along with that. So apologies for not telling you guys that.
No, sorry about that one, everyone. So just some quick settings to go through. So we have layer thickness and variable layer height. So we have a sphere, and so if you notice on this right-hand side, we have sort of cross-sectional view of the different layer heights present in this model. So at the top here, it's green, and you can see it's kind of gone there. And it's kind of hard to tell, but there's layers here which are a lot thinner than these layers. And so that's useful when you have areas of high curvature, like the top of the sphere, and it produces a much better print. And so you can do that using this setting in the top right. And then you can, using these sort of guides, you can then say if you want the middle bit to be a little thicker, you can then right click, and that should remove the detail. And it's relatively straightforward. And then you can also just reset if you've made a mistake. And then, oops, that one. So then also infill pattern. So this is probably a really big setting when you print. So infill is the amount of material that's inside the model as you print it. And then infill pattern is how it's filling that model. So on the left here, we have a gyroid pattern at 15%. And so you can sort of see it's filling it, but it's not as full as over here, which is 100% and rectilinear. And so gyroid, it's sort of going back and forth in these squiggly lines. Whereas here it's just going back and forth in straight lines all the way across. And then the result of this is print time and filament usage. So if you look on the left, there should be the internal fill, which is about 50 minutes for this. And over here, the internal fill is about 3 hours. So just by changing the infill and the type, we've added on 2 hours to our print. And so you should only really be doing that if you need to. So if you need something that's super strong, then you might want to go with 100% infill, or in the medical case, when you're doing a CT scan, it's a lot easier to calculate when it's 100% infill because it's all one material and you don't have to worry about air gaps. I believe Andrew? Yep.
Yeah, okay.
There you go.
So this was kind of going to be the interactive bit. It would have helped if I told people to bring their laptops along. For you that do have your laptops, so open Prusa Slicer and you should have something like that on the right. And also, guys, if you have any questions, don't worry. You can ask them like right now. You don't have to wait till the end. Yep. So once you've got the slicer open, has anyone here downloaded the CaliCat model that Pejman sent out in this? You did? Okay, cool. We got one person do it. It's great because I did want to kind of get a print going during the workshop of someone's own Gcode just to show you how easy it is. And it really is just a few steps. I'll show you now. So first of all, you import the model by clicking that cube with a little plus. Any model you ever want to import, it's the same thing. And then once you've clicked that, it'll open up a file directory, and then you can choose which model you want to print. So we're going to print these CaliCats. As I said, I've got a few of them here. And once you've clicked on that, you should have something like this in your slicing program. And as Riley showed you before, it's the same for any model. So the holo dodecahedron that he had, any model will pop up like that. You can change the size, positioning, and it actually is quite important to change the orientation of your model on the heat bed. So that is how it will print, just as it's visualized from the bottom up. And I have some failed prints here, failed prints are great because you actually learn from them. But you can imagine how I felt after about 10, 12 hours of printing, and then you get that on the side. That's meant to be nice and perfectly smooth. So I came in the morning after a long print. It was looking good the whole time, and I ended up with something like that. And so the reason that this happened, there's a few reasons. This thing's actually hollow. There's no infill in the middle. And because I had it orientated like that on the print bed, when it got to the top, it has to come straight across from the perimeters. And it just can't do that with that kind of geometry. Now, the fact it's hollow wasn't the main problem. It's the orientation. If I print it like that, it can go straight across. And it did. For one of those cubes there, or those quadrants, it's totally hollow. And it can go straight across. It's called bridging. Riley will talk about it in a second. So yeah, I just wanted to mention that. The print orientation is very important. And you get to learn that over time. And I guess it's a bit of intuition too. Alright, so if anyone does have a CaliCat model or any STL model, I think you said you had one, and you get it in like that, we're going to use these print settings. 1, 2, 1, nice. We're going to use these print settings that are optimized for speed. 0.3 millimeter layer height, don't know if you can see that, but that is the biggest layer height, so the lowest resolution, and it's going to be the quickest print. And other settings, so we have 10% infill. If you can do that, that's pretty quick. You can go any number. You can do 1, 2, 10% is going to be pretty quick, especially for this small model. And then I've scaled the size down to 90% just to make it a little bit quicker. So what I was hoping to do was actually get some of these printing so you guys can see the whole process. See it warm up, see it calibrate, Pejman, do you think it would be practical if we could get 2 groups coming up to the front? We'll get one working with Riley. If you want to start a print on that one, there's a CaliCut model loaded onto that. Yeah, and then I'll have another group here. So if you could split into halves, and we'll show you the whole entire process so you can see it up close and know what to expect when you do your first print. Alrighty, yep. So guys, come nice and close. Oh, can't promise about Riley. Yeah, okay. I'll just have to get this guy over here because this was the one we're going to get the Gcode. Is it right if I get you over here so we can print yours on this one? Yeah. No pressure. If it doesn't work, blame it on the printer. That's what I do.
I can't get 0.3.
Where's that? Oh, okay. Yeah, so yours is an older version. That's fine. 0.25 will do fine. And then scale it down to 85%. So yeah. So yeah, guys, if you can look at the screen too, that would be good. So we've got it on 0.25 millimeter layer height. This kind of older version doesn't have 0.3, that's fine. 0.25 is quick. 20% infill, so if you want to click that one there and change that down to about 10%, that will be a bit quicker for us. Yep. And then all you need to do is click slice. So absolutely no coding whatsoever. Yep. And it will give you a bunch of details. So you can see print time, 33 minutes, and see this dial here, grab that just there, that little arrow top, and bring it down. You can actually analyze what layer by layer what the printer's going to do. So it starts from the bottom and it goes to the top, and this is great. If you have a complex model, sometimes there are parts that are not connected to the model when you're looking from the bottom up, and the printer will just go over to that area and start trying to print it in the middle, and it will fail. And you'll need to add supports to that. Riley will talk about that later. But that's awesome. So you've got that, and you're going to hit export Gcode, and we're going to chuck it on this USB. If you can put that into your, just here. Got it in the right way. Yep. So yeah, it's really easy. You chuck in your USB. This one uses a USB. The other one uses an SD card. Yep. So it's exported. Cool. And then we'll just chuck it in the back here. And it will show you the latest thing you added, obviously, if you don't want it to go back. And yeah, you click print. So I've already preheated this for PLA. This is the filament we're using here, which means this heat bed here is going to go up to 60 degrees. You can feel it if you want. It won't burn you at 60. Yep, just give it a little feel. That there is a bit of a mess. Usually we'd chop that at the start, try to get this filament off. Just pull that off. You don't want to get too close to the extruder head. Right now it is at 170 degrees. After it calibrates, it's going to go up to 215 degrees. So right now what it is doing is it's probing 16 discrete points along the bed, and it gets an idea of the leveling using the probe on the side of the bed. So if it gets a little bit deformed when you take it off and you're taking off your prints, it doesn't matter, it will compensate for that across the whole entire bed. So that's called I think it's auto mesh bed leveling, something like that. That's something that only some printers have. These Prusa ones are really good, they have that, they've always had that, and some of the cheaper ones don't. So after that, it's done it's heated up, it's done its little calibration. What it's going to do is it's going to heat the extrude head all the way up to 215 degrees for PLA. Now if you're working with ABS, I think it's going to be something higher, I think it's 240, something like that. But you don't have to remember them, because when you choose the filament type in the slicing program, it just does it all automatically for you. So yep, that's going to heat up now, and then it will start. And the first thing you'll see is it's going to extrude one line along the bottom. Yep, and that's trying to get rid of any of the mess that's attached to the nozzle. And it will start on the print, and hopefully it will start well. And so whenever you print, you really want to watch your first layer. And I'll get into that on another slide. I'll stand over the side so you can see. You really, really want to watch that first layer, because if your first layer fails, your whole print's going to fail. And I've had prints before I've walked away before the first layer's gone down. The first layers came off, and I've walked back and it looks like a bowl of spaghetti. Because what it does is this printer doesn't know, it's just going to print in midair, and it's just going to be it will look like a bowl of spaghetti. So right now that's looking pretty nice. I'll get into what looks good and what doesn't with your first layer in another slide, what to look out for. But yeah, that's looking great right now. And then it's in another slide too, but I'll just show you while we're here. You click Tune, simply live adjust Z, and from there, that's when you can adjust the distance that nozzle is to the heat bed. I think hundreds or thousandths of a millimeter, just really, really precise. And so you can ask Riley, I spend way too much time playing along with that. He gets a little bit frustrated, but it's really good to get that perfectly precise. It's going to affect every single layer from the bottom up and just give you a really great print if you can get that calibrated. So that's really the only manual thing you have to do yourself. And yeah, there's a few other settings you can adjust while you're at it. You can do the speed, you can dial that down or up. If you've got a bit of a more complex print, you might want to dial that down. You can do that in the slicer too. But when you're doing your first prints, just leave it as it is, and it should be fine. So we're just probably going to get back into the PowerPoint soon. We are running out a little bit of time, but I think this will probably finish by the end. Yeah. And then you can have the cat that prints, so that's a bonus.
Did you mention to clean the surface?
Yeah, I got that in another slide coming up.
And so when you select it, there's a lot of like, because these aren't supposed to be perfect like diameter levels, but there's obviously some variation depending on the manufacturer. And so Prusa Slicer can take that into account and use better print. Because it's in contact with these wires and then all that information.
Alrighty, might get back to it soon. How's yours looking?
Yeah, I didn't print the cat.
Oh, that's fine.
It's the
That's
wrong
fine.
one, but it's still about 36 minutes,
Yeah.
so it'll be fine.
No, that thing's pretty cool too. That's yeah,
That's the disc holder, right?
yeah.
Just a question.
Yep.
On the material you used to print with,
Mhm.
how safe is it in
Yep.
terms of fumes and?
So PLA, this one's really safe and it's actually biodegradable. So if this one goes in the ocean, it will break down on like your plastic bags or anything like that. So yeah, PLA is a great filament to use, a great beginner filament. It doesn't screw up as much as something like ABS does. ABS, if you ever get a hold of that filament, it will release a fume that I don't think is toxic. I think they call it an irritant though, so it will give you headache and so on. But yeah, this filament is fine. But you can get a lot of different filaments, and it's very important that you read up on your filament before you start printing, because I think there are definitely some toxic ones. Yep, there's some filaments, they mix with stone, some other things, and you actually need to get a different extruder head. It need to be, this one's brass, it will need to be something a bit stronger to deal with that really tough material. But yep, this one melts about 60 degrees, I think, 60 or 70. Once you heat it up past there, it will start melting. But yeah, all right, we'll get back into this.
Just a note on the PLA, it's also biodegradable, so it doesn't like cause any irritations to when it comes to the skin.
Yeah, it's a really great filament, especially to start off with. All right. Sure.
Cheers. Okay. So Andrew mentioned a bit earlier, bridging and overhang. So bridging is when it prints across just a gap. So as this printed from the bottom up, these two supports would exist, and then it would have to, when it got to this layer, it would just have to print straight across. And so these printers can do it, but as the bridge gets longer and longer, it starts to sag and the quality goes down. So this is actually a test model, so you can test like how long your bridge could be before it starts sagging, for instance. And this is important for like, so when you're printing the cats.
It's actually bridging right now, as he's speaking.
Yeah, so like the tail, for instance, that would be bridging because it's just printing, actually, sorry, that'd be overhang because it's not attached at the other side. So overhang is when it's angled and there's no like wall for it to bridge to. It just has to print at this angle. And so most of these printers have an inbuilt setting of about 55 degrees is where they sort of call it and go, we can deal with overhang of about 55 degrees, but anything more and it just sort of stops and you need to start supporting it. Speaking of supports, so when you make a model, you might need to add supports because like the hollow dodecahedron that I showed, that might just be too weak to actually print as it is. So for instance, does anyone want to guess what this actually is through the supports? Can anyone figure it out? Bonus points, extra marks, anyone? So this is actually half a pelvis. So as you can imagine, or a pelvis has just a lot of air through it. Did you say that? Oh, no, okay. So there's a lot of like air, and so to actually print this and have it so it doesn't just completely turn into a mess, you'd have to add all these supports. And so if you look at actual print, so external perimeter, infill, that's about an hour, 2 hours, but the support is 6. So this is taking up a good chunk of your print time. And so by doing ways, discovering ways to reducing support or cleverly placing supports, you might be able to reduce this 6 hours to say 3. And so when you're making supports, there's sort of 2 methodologies you can use. So there's, you can either enforce a support, or you can say we don't want any supports at a certain area. And so you can say support everywhere except for these areas, or only support these areas. So it's sort of like one side of the same coin. It's really just personal preference. I typically like to do the enforcing because I can specifically control it and it's a bit easier and quicker in my mind, but it's up to you guys. So some inbuilt settings. So these are sort of things that just sort of exist in the software. When you decide on like the speed settings or quality settings or draft settings, these are all just automatically picked for you. And so you don't really have to worry about them except for in like really specific cases where you think that the speed might be affecting your print or the acceleration might be affecting your print. And so there's a bunch of like these sort of things, or like temperature. The Prusa slicer has inbuilt the filaments, and so if you say PLA, it'll automatically go, oh, that means the extruder needs to be 210 and the heat bed needs to be 60, I believe. So these are all just sort of things that are there, but you never really have to go into them. So just sort of good that you see them more than anything. So Brim Rough, so these are a bit more advanced. So this is Brim over here, and so that adds an extra couple layers to your print, and this helps it sort of stick to the bed a little easier. And then here we have Rough, so this builds out a couple layers before it then starts printing out your print. And so these all help with first layer adhesion, which I believe now Andrew will be talking about. There you go.
Cheers. Alrighty. So yeah, for those of you that were over here, you would have heard me talking about first layer adhesion. So I think this is probably one of the most important points to get down. So of course each layer is built off the last one, and if you get a poor first layer, the rest of your print's going to be poor. And as I said, if your first layer actually comes straight off the heat bed, it doesn't have anything to print onto, it's going to be printing in midair, and you'll wake up after a long print to spaghetti. And that's happened to me, it's not good. So I'll go over it a little bit more, how you can tell if you've got a good first layer and so on. Alright, yep, this is a good one. So there on the left, that there is a case of the nozzle being a bit too high up from the heat bed. And this is really something you want to look out for. So what I recommend is when you first get to a printer, if it's not calibrated, which is what I spent a lot of time doing when I was learning with these printers, when we first got them, they weren't quite calibrated or optimized. It's just printing out a square, just maybe one layer or 2 layers, and then you want to look at the pattern that you can see. So that there on the left, it's too high. The nozzle is too high from the heat bed, and what happens is it doesn't push the filament out and across. And so you get this fanning effect where the layers actually aren't connected side by side. In the middle, that's perfect. If you got that, don't touch the printer. It's happy. If you get it out of the box and you get that straight away, that's just amazing. And then this is the worst one, too low. If it's too low, first of all, you can get scratching of the heat bed. The nozzle can scratch it. It can damage the nozzle, it can damage the heat bed, and it can push the filament back up into the extruder, or hopefully off to the side, but back up. It can cause a clog, can cause damage downstream on the printers. That actually happened to this one recently. Had to disassemble part of the tube, and it's really annoying. So yeah, make sure you have that really good first layer, and I'll give you a few tips on how you can achieve that. So first of all, the heat bed has to be clean. So yeah, you saw me touching it and feeling the temperature of it. You probably shouldn't be doing that, but it's nice and warm and it feels good. So with these ones, they're coated with PEI. It's really chemically resistant, and you can wash it with just something like a dishwashing liquid. But if you have a different heat bed, some of them are glass heat beds, I'm sure that would probably be fine with that. But you should look up how to properly wash it. But in my experience, this has been fine. And I have had times where the first layer wasn't adhering, it was coming off, and then after a quick wash, it's all it needed. Yep, so if it's severely scratched over time, that's obviously not gonna help. It's got to be as smooth as possible, so look out for that. Yeah, so the heat bed temperature. So if you've put in the correct filament setting into your slicing program, that will all be automated. You don't have to worry about that. But if the temperature of the heat bed is, say, too high, you can get not just a poor first layer, but you'll have something like that. It's kind of small, isn't it? That's called elephant footing, where it droops at the side. And so it's definitely not something you'd want. And if it's too cold, then the print's going to cool down too quick and it's going to snap off your heat bed. So just make sure you've got the correct filament in the slicing program. Really, that's all you have to do. Occasionally, I've changed the heat bed temperature up just a teeny bit. I think it makes it adhere a little bit more. The extruded temperature, similar story. It's all automated for you as long as you've got the correct filament in there. If the extruded temperature is too high for your filament, so if you've got it set for ABS, which is much higher, and you're printing out something like PLA, it's going to be in a really molten state, and you can't do things like bridging and overhanging that Riley was talking about. It's going to be way too sloppy. And if it's too low, the plastic will still come out because it melts at about 60 degrees, I think, this one, but it won't be melted and molten enough for it to actually adhere to the heat bed. So yeah, just make sure you have those settings correct in your slicer. And then, as I said before, the nozzle to heat bed distance has to be optimized, and that's the most important thing. If you take away anything from this, have a dirty heat bed, have it scratched, whatever, make sure this is correct. And so I was showing the guys over here how to do that. There's Live Adjust Z in the tune settings. And as I said, you just print out a simple square, something like that, and make sure you have something like the one in the middle. And so
Cheers. So obviously first layer adhesion, that's not the only thing that can go wrong. We can have layer shifting, warping, stringing, or just filament clogs. So layer shifting, so it's like the staircase effect. So this is typically caused by mechanical issues with the actual printer. So as it prints, the printer sort of loses track of where it is and moves over a couple mils. And so then then this layer might not be exactly printed like on top of this layer, and so on. And so it can slowly start to sort of get away from you. So the way to fix that would be just sort of checking each of your components, so each axis, the heat bed, sort of mechanical issues, because that's typically the cause of this problem. Warping, so this is usually, this is when the heat bed, this is when the corners of your print sort of pull up from the heat bed, and this is typically caused from a difference in temperature between your actual print and the outside ambient air temperature. So as it cools, the edges get more exposed to air, and so that causes it to contract, so it pulls up. A way to get around that is using Brim or using Andrew's first layer adhesion techniques to make sure it really sticks and so it doesn't change the shape of the print. Stringing, so this is where some excess filament sort of comes out as it's moving around the print, and so that's those like stringy bits. To sort of solve this problem, we need to you can decrease the temperature of your nozzle just a little bit. That way less filament actually comes out as you print, and so there's less material, and so then there's this excess material isn't coming out. Another way is to implement a dry box. So sometimes this is caused from moisture in your filament that's sort of bubbling, causing a change in the amount of filament coming through. And so that would be under the sort of accessory side of the 3D printing. And another one is filament clogs. So this is just your extruder head gets clogged with filament, and so the right amount can't come through, and so you might be overheating, or there might just be not enough for each layer. And so to solve this, you need to sort of poke a needle that comes in the kit that comes with the printer, and so you can sort of scrape out this excess filament that's stuck in your head. And so these and along with other problems exist in 3D printing, and so Prusa has a help site you can go to, so the address is down there. And so you can just go in, search the knowledge base, so you might want to type in stringing, what do I do? Or if you ever want to make any adjustments to these actual printers, so like any of those mechanical fixes I was talking about, this website will take you to an article and that'll guide you through it step by step. And so it's very helpful for when you want to fix a problem with your printer. I believe now that's Andrew.
that site's really good. I know sometimes in presentations people check this site out or whatever, and you're like, yeah, right. But if you do ever run into any of these problems, the best thing is, if you don't know what the problem's called, you just type in the description of it into the internet, and someone would have had that problem, and then, go to Prusa's site. Alright, so making your own models. Unfortunately, this is not a guide. Making your own models is a lot harder than the printing process itself. Could do another workshop on that. But yep, I will go over a bit of an overview. I'll show you guys which softwares are good to use if you want to have a bit of a play around with them anyways. So in general, there's two kind of types of 3D modeling. There's parametric and then non-parametric. So parametric is where you're very precise. Each object is defined by its orientation and its dimensions, and there's constraints with respect to each of the other objects. So in the parametric modeling software, if you made one part of it bigger, the other part might increase with half that scale or something like that. So there's an example on the right there. It's in Fusion 360. I didn't model that up. I wish I could. It's really cool. But yeah, so that's extremely precise. And as I said, used more in engineering fields, but I've definitely printed stuff out that was modeled up on Fusion 360. A little bit simpler than that. And then so you have non-parametric, which are used to create models that look nice, really. And then so at the bottom right there, you can see an artist interpretation of an Egyptian mummy. And that's kind of the process, I guess, an animated process and the steps he took to make that. I don't know how to do that. So the things I do with Mesh Mixer and Blender is more kind of manipulate those 3D objects from CT files to make that phantom that I showed you before. So I definitely can't do something like that, but I will go into why you want to use a non-parametric modeling software over a parametric modeling software. So yeah, to manipulate the STL objects, so any of the ones you download online, the CAT, any of the ones that are made on Fusion 360, you're going to have to use something like Mesh Mixer. So before today, I actually didn't know you can do it in Fusion 360, but it's just not as extensive. It's not designed for that. And so you're going to want something like Mesh Mixer. And if you do want to play around with that, that's a great program to start with. The two big ones is Blender and Mesh Mixer. But Mesh Mixer is a lot simpler. They're both free to download, so you can do that. And if you want to play around with a parametric modeling software, I think Tinkercad's a really good one. It's free, it's online, you don't have to download it. And the only problem is there's quite a few limitations to what you can do parametrically. It is 100,000 times weaker than something like Fusion 360, but Fusion 360 is a bit more complicated. Fusion 360 is actually available for a 30-day free trial, I think, for anyone. And students can get it for free, I think, for a year or two, something like that. So that's great if you want to hop around on that and just have a little bit of play with parametric modeling. That's probably one of the best softwares to do so. I have a friend, he uses SolidWorks to do all his 3D modeling. I've never used it, so I can't say anything on it. But get Fusion 360, I think, if you're going to want to go with something that's parametric modeling. And that's it. Any questions?
Why are you talking about the supporting materials? Are the supporters like detachable?
Yeah. So you want to pass the mic?
Yeah, sure thing.
Cheers. So when you, in one of the settings, you can define how much of a gap you have for the like support snappers essentially. So they're just like extra weak points that are on the material. So it can be like 0.5 mil, 1 mil. And so that's like how you're going to detach them essentially.
Yeah, there's like a plethora of settings.
Yeah, so you can see this dark green, those are the bits that like detach. And then you'll also notice that it's built so it zigzags in a specific direction, so it's actually weak along there, so it's a bit easier to like destroy.
Yeah. There's heaps of different like patterns of support. Yeah. Yeah, pretty sure. So yeah, you can change that. So you can choose a support that's like stronger or weaker, I'm pretty sure, to break. But yeah, you won't really be changing any of those settings. If you can, you want to try orientate your print such that you don't need supports, or the least amount that you need. They are really annoying to remove, and especially if you're doing them in between really thin parts of the object, you might actually break off a part of your print. But sometimes you just have to use them. So it prints from the bottom up, and if you can imagine, I'm holding something over like that, where it will print my foot first, and then this will be attached to something higher up. So it can't print this part first, right? Or else it will be in midair. You'll need to put a support there. And so it's good when you're in the slicing program. You go layer by layer. On the right, there's an orange dial, and you can actually see the steps that the printer would take. And if you see just something pop up in the middle of the air, it's going to ruin your print, and you need to put a support there. So yeah, supports are a huge part of 3D printing. Yeah. Any other questions? Anything at all?
For starters, would you recommend the mini or would you recommend the
To work on or to buy?
to work on?
To work on, that one. It's a lot more stable. You run into problems way less. This one here, some 3D printing expert, he came in the other day and told us the detectors that they put on this one, they cheaped out a little bit, and they're not temperature dependent. So they basically detect the distance using electromagnetic induction. The properties of it changes with the temperature of the heat bed. And so depending on when you calibrate it, it will have a different kind of calibration. So that thing can be a bit dodgy, and I spend a lot of time always changing that. So I'd definitely go with that printer if you wanted to start learning on it. Yeah, and it's bigger. So, yep. Yep. Yeah, okay. So off the top of the head, it's over $1,000 AUD, under 2,000. I think probably around 1.3,
Something like that, yeah.
somewhere around there.
Most of the prices are quoted in USD.
Mm.
So like you see those and go, that's not that bad. But then you get the convert it, and I know.
Yeah, you can kind of trick yourself into thinking it's cheaper than it is.
Yeah.
But this one maybe around 700, 800 AUD, maybe 900 these days. I think they used to be a little bit cheaper. But as they release more printers, obviously these ones will get cheaper. They're releasing 4 new printers this year. So 2 upgrades and then 2 totally new ones. And if you want your own printer, I mean, these are great. And if you have that kind of money, then yeah, I definitely would recommend these. You can get printers that are around $300, $400. They don't have the auto bed leveling like these ones do. But my friend's got a printer for $350. Perfectly fine, same kind of print area as that, and he gets some nice prints out of it. So yeah, it's kind of a fun thing to do. Yeah. Any other questions? No? All right then, we'll wrap things up. And if anyone wants to come to the front, check these prints out at the end. You can have the cat if you want. You can see how they're going and how they went. Feel free to do so. All right, thanks guys.
Thanks for listening.